You need to understand this up front. The Parker Solar Probe didn't just observe the sun from afar. It entered the sun's outer atmosphere, the corona, and sent back in situ measurements from inside that environment. At closest approach, the probe reached distances on the order of 6 million kilometers from the photosphere, well inside the region where plasma is heated to millions of degrees, and where the solar wind is born. That fact alone changes everything. Instead of inferring what happens in the corona, we now have direct measurements of its plasma, magnetic fields, and microstructure. Inside the corona, Parker found a level of complexity that is hard to overstate. Instruments recorded sudden, large amplitude fluctuations in plasma velocity and density. They recorded magnetic switchbacks, abrupt reversals in field direction, and localized jets where plasma velocities spike by significant fractions. These were not ephemeral blips. Many of these features persisted long enough to be tracked as they moved, indicating coherent, transportable structures rather than mere background turbulence. When you hear the corona is chaotic, that is true in one sense, but Parker revealed coherent chaos, organized structures embedded inside turbulent flow. This matters for the question you clicked on. Coherence suggests the possibility of stable plasma configurations. Plasma is electrically conducting. It couples to magnetic fields, and under the right conditions, it self-organizes. Laboratory plasmas form filaments, vortices, and solitons. Space plasmas can, to Parker's data, show precisely those kinds of ordered behaviors at coronal scales. Because the corona is collisionless and magnetized, nonlinear processes can produce structures that maintain identity for long timescales relative to local flow. Those are the building blocks of what some call plasma entities, not biological life, but persistent, self-contained electromagnetic structures that act like objects. So Parker didn't find life. It found physical structures with longevity and coherence. Switchbacks, waves, jet trains that shift our baseline for what structure even means in the sun's atmosphere. This is the experimental foundation. Before we call anything an entity, we must catalog how long these things persist, how they form, and how they transport energy. Parker gave us the measurements that let scientists ask those questions with data, not speculation. Keep this in mind as we move to the specific structures that look the most intimate: switchbacks, solitons, and real plasma organization. You've probably seen the phrase magnetic switchback a lot here. That's exactly what it means and why it matters. A switchback is a sudden localized reversal of the sun's magnetic field that travels with the plasma flow. Imagine the field line folding back on itself like a kinked rope. When that kink moves outward, it carries a bundle of plasma with it. Parker encountered these repeatedly, in clusters and trains, often accompanied by rapid velocity spikes. That repeated structured occurrence is our first real evidence of plasma features that behave as discrete, mobile systems. Why is clustering important? Because random turbulence produces scattered, short-lived fluctuations. Clusters imply a production mechanism and an internal coherence that allows features to remain distinct as they propagate. The leading explanations involve magnetic reconnection near the solar surface, closed loops snapping open and ejecting compact packets of magnetized plasma, but observationally, the result is the same. The corona contains magnetically bound packets that travel and interact like objects in a fluid. In addition to switchbacks, Parker has measured alphenic wave trains and signatures consistent with soliton-like structures, nonlinear wave packets that preserve shape over long distances in other branches of physics. Solitons are known to act like particles of the medium. In a magnetized plasma, soliton analogs can act like self-sustaining packets of energy and matter. Combine switchbacks and soliton-like wave packets, and you have a system capable of self-organization. Fields and currents that produce stable geometry, maintain internal coherence, and transport energy efficiently. Instrument data show these packets can travel thousands of kilometers, interact, merge, and dissipate behaviors you'd expect from objects in a plasma medium. Again, this is not biology, it is physics that produces object-like behavior for the scientific question at hand. The critical points are persistence, reproducibility, and measurable dynamics, all of which Parker has provided. So when you ask, do plasma entities exist near the sun, the data shift the question from fantasy to testable hypothesis. Parker found phenomena that satisfy key criteria for being treated as coherent entities: repeated formation, measurable lifetimes, transportability, and interaction dynamics. The next step, which researchers are actively pursuing, is to map formation sites, quantify lifetimes, and simulate the processes to see if these structures can emerge naturally under coronal conditions every time the sun behaves a certain way. That's the frontier you're watching. Listen closely. If something in the corona behaves like an entity, it won't look like a creature. It will look like a coherent physical structure with measurable boundaries, internal fields, and predictable motion based on Parker's insight to data and coronal imaging. The candidates for entity-like behavior are plasmoids, magnetic flux ropes, and solidone-like wave packets. Here's what each of those looks like. In the real measurements you'd expect to see, a plasmoid is a compact island of plasma and magnetic field formed during magnetic reconnection. In images, it can appear as a bright knot or bubble moving outward. In in situ data, it shows as a localized reversal or enhancement in magnetic field strength, a density pulse, and coherent velocity. Plasmoids form in current sheets, the thin layers where opposing field lines break and reconnect, and they can range from kilometers to thousands of kilometers, depending on where they form, because reconnection is common in the corona. Plasmoids are a natural byproduct. They're discrete, travelable, and persist long enough to be tracked by instruments. A magnetic flux rope is a twisted bundle of magnetic field lines threaded with plasma. Flux ropes have internal topology, distinct from surrounding plasma. You can detect them by their rotating magnetic signature. Organized current systems and tightly correlated plasma and field changes as they pass a spacecraft. Large flux ropes are already observed in ejecta and coronal mass ejections. Smaller flux rope analogs can exist continuously in the corona and appear as persistent. Object-like structures, solidone-like wave packets, are another possibility. These are nonlinear plasma waves that preserve their shape while moving. In the corona, they would show up as repeated stable pulses in field and velocity data, and as coherent brightness features in cadence imaging. Solidone behavior is attractive because it supplies a physical mechanism for long-lived, self-preserving structures without needing a rigid body. Crucially, these forms have measurable fingerprints, correlated magnetic field rotations, density and temperature contrasts, velocity coherency, repeatable lifetimes, and predictable propagation speeds tied to local alpha speeds. If you treat them as entities, it's purely because they meet the operational criteria of object-like persistence, self-organization, and interaction. Not because they're alive. In short, the corona already produces structures that behave like objects. Calling them entities is shorthand for coherent, stable plasma configurations you can detect and model. You're smart to ask, how do we know these observations aren't just noise, image tricks, or instrument glitches? Scientists separate real structure from alternatives using cross-checks, multi-instrument correlation, and theory-driven predictions. Here's how that process works and what it's already shown. First, multi-instrument confirmation is essential. Imaging SDO, SOHO, WISPR on Parker shows morphological features in motion. In situ instruments fields for magnetic fields, SWEP for particles. Supply the local plasma and field signature as the spacecraft crosses the structure. A real plasmoid or flux rope will produce both a spatial brightness feature in images and a time series signature in the probe S measurements. When those line up in time and direction, it rules out single sensor artifacts. Second, the signature pattern matters. Random turbulence produces a broadband. Stochastic signal coherent structures produce ordered fingerprints, smooth field rotations, flux rope, sharp but localized density, velocity pulses, plasmoid or repeated, shape-preserving wave packets, solidone-like. Scientists use statistical analyses to show that the observed switchbacks and pulses exceed expectations for random turbulence in amplitude, duration, and clustering. Third, predictive modeling and simulations are used to test hypotheses. Magnetohydrodynamic MHD and particle in-cell PIC simulations reproduce reconnection, plasmoid formation, and solitone propagation under coronal conditions. If simulated structures produce the same multi-sensor signatures and dynamics we observe, that strengthens the real structure interpretation where simulations fail. The hypothesis is revised forth. Alternate causes are constrained. Projection effects from line-of-sight imaging are tested by comparing viewpoints, e.g. Parker's, WISPR, versus Earth-based coronagraphs. Instrumental artifacts are eliminated by cross-checking independent instruments and spacecraft. If two different spacecraft separated in space see compatible signals, It's not a local glitch. Finally, targeted tests are ongoing. Map where structures form active regions, coronal holes measure lifetimes, and energy budgets, and test if the structures interact like discrete objects merge. Bounce, fragment future campaigns, coordinated observations with Solar Orbiter. DKIST and Parker are designed specifically to test formation mechanisms. So what would convince scientists? Consistent imaging plus In situ signatures plus reproducible simulation results plus repeatable formation sites, that's the bar. Right now, Parker's discoveries pass many initial checks. Coherent switchbacks, clustered pulses, and solidon-like trains exist in the real data. The work going forward is turning those observations into robust physical models that explain how, where, and why the corona produces these entity-like structures. This isn't just academic curiosity. If the corona routinely produces coherent plasmoid and flux rope-like structures, it changes core assumptions about how the sun heats its atmosphere and accelerates the solar wind. For decades, we've debated where the corona's energy comes from and how the solar wind reaches observed speeds. The presence of persistent, mobile magnetic structures offers concrete transport mechanisms. They concentrate magnetic energy, convert it via reconnection, and shuttle that energy outward as coherent packets rather than diffusing it as random turbulence concretely. These structures provide targeted sites for particle acceleration. When a flux rope or plasmoid forms and reconnects, it produces localized electric fields that can accelerate electrons and ions to high energies. That matters for radiation-risk spacecraft, astronauts, and even high-flying aircraft can be exposed to sudden particle bursts originating from compact coronal events. If switchbacks and solidon-like packets seed the solar wind with energetic particles, forecasting those bursts requires tracking those structures from formation to escape. They also affect mass and momentum transport. Rather than a smooth laminar outflow, the solar wind becomes patchy, bundles of plasma moving faster or slower, carrying different compositions. That explains why in situ measurements show sudden velocity spikes and compositional heterogeneity for planetary space weather. This heterogeneity changes how magnetospheres respond. Earth's magnetosphere may see intermittent impacts with higher dynamic pressure or altered magnetic orientation when a plasmoid hits, triggering geomagnetic From an energy budget perspective, coherent structures concentrate dissipation where and when it matters instead of distributed heating. Localized reconnection and wave dissipation inside these entities can efficiently convert magnetic energy into heat and kinetic energy. That offers a scalable mechanism for coronal heating that aligns with Parker's observations of concentrated events. So, when you watch the data roll in, know this. Finding object-like plasma structures is not a sidebar. It's central to resolving how stars like our Sun move energy and mass into space, with direct consequences for understanding stellar winds across the galaxy and protecting technological infrastructure here on Earth, detecting and validating. Coherent plasma structures requires a coordinated toolkit. First, in situ measurements from spacecraft that physically pass through the structures. Parker's fields and SWEP instruments give direct magnetic, electric, and particle signatures, the hard proof of a passing plasmoid, field rotations. Density pulses, velocity spikes, but a single spacecraft can't prove a large 3D shape. It samples a time series. That's why coordinated multi-platform campaigns matter second. Remote imaging ties signatures to visible morphology coronagraphs, SOHO, stereo, WISPR, on Parker, and ground-based DKIST images show brightness features and motion. If an image feature moving outward lines up in time and direction with local in situ signatures, you've localized the structure spatially and temporally. Add spectral imaging and polarimetry to measure composition and field geometry remotely. Third, multi-spacecraft geometry. When two or more spacecraft at different vantage points record compatible signatures, field rotation, particle flux increases, and matching imaging, you can reconstruct the 3D shape and trajectory. Solar Orbiter plus Parker plus Earth observatories together give parallax and multi-scale coverage. Fourth, data analysis methods, cross-correlation, wavelet transforms, minimum variance analysis for fields, and particle distribution fitting extract coherent signals from noisy backgrounds. Machine learning is now used to classify events switchback versus turbulence versus Instrument glitch, and to find repeatable patterns across large datasets. Fifth, laboratory and numerical experiments, MHD and kinetic pick. Simulations reproduce plasmoid formation, flux rope dynamics, and solitone propagation under coronal conditions. Laboratory plasma devices recreate scaled reconnection and plasmoid physics, providing controlled comparisons. Finally, targeted campaigns, scheduled conjunctions of Parker Solar Orbiter, DKIST, and coronagraphs are now designed to catch formation regions at the Sun, while another probe samples the outbound packet. That observational choreography is essential for turning episodic detections into robust science. If you follow the feeds, look for joint press releases and coordinated data drops. Those are the moments when a suspected entity becomes a scientifically confirmed structure. Here's what the instruments are picking up, and it's not subtle. Images show the coma expanding. Photometry shows the light curve rising sharply. Spectra show volatile gases increasing by orders of magnitude. Everything lines up with a single story. 3I Atlas is venting material faster than anyone expected. The numbers tell the story. Brightness doubled in under 2 weeks. The apparent size of the coma expanded to over 24,000 kilometers across. The tail lengthened as new dust streams formed, each one pushed outward by radiation pressure. None of that is hypothetical. It's straight from multi-observatory imaging sequences. Then comes the spectroscopy, the real smoking gun. Telescopes like Keck and the Very Large Telescope picked up stronger CN bands, confirming intense cyanide outgassing. But they also detected something unusual: metallic lines, especially nickel. Near the core, that's not common in most comets. It suggests 3I Atlas contains metal-rich grains that vaporize under extreme solar heating. You can literally trace the physics. Nickel and cyanide emissions: spike gives gas, expands gives coma, inflates gives brightness, skyrockets. Each variable confirms the next. We've also seen changes in tail geometry. The anti-tail that formed earlier began to shift direction as fine dust particles were blasted by the solar wind. Smaller grains got pushed into a thin, straight tail. Larger ones stayed behind, forming faint streams near the coma. That evolving structure is how you see radiation pressure acting in real time, and there's one more measurable side effect. The comet's path is drifting, not from gravity, but from the sheer push of gas escaping. That outgassing produces a non-gravitational acceleration that's visible in precise orbit data. It's tiny, but consistent proof that the ejection forces are strong enough to nudge a multi-kilometer body through space. Put all of that together: the spectral spikes, the rapid coma growth, the altered tail geometry, and the measurable trajectory change, and you get a complete physical confirmation. Solar activity didn't just illuminate 3I Atlas, it changed it. July 1st, 2025. Atlas flags a faint, fast object. The software and team run the numbers, and within hours we have an eccentricity. 1. This ISNT, a solar system comet observatories, kicked into gear fast. Within a day, the Minor Planet Center and JPL had orbit fits, and telescopes worldwide began queuing target of opportunity observations. What mattered next was cadence. Over the following weeks, the light curve did not creep up, it jumped. Photometry from survey telescopes and follow-up imaging showed a flux increase measurable on day-to-day frames. That's the first timing flag. Abrupt brightening while the object was still at large. Heliocentric distance teams compared archival frames. Then started coordinated spectroscopic runs. Hubble, JWST, Keck, Gemini, and several ground spectrographs took prioritized data. Those rapid follow-ups are why we can say the brightening is instrument-backed and multi-wavelength. The imaging showed the coma expanding to tens of thousands of kilometers. Spectra showed volatile and metal lines strengthening at nearly the same time. Perihelion timing matters for interpreting behavior. The object is moving inward, and the main heating windows happen in the weeks surrounding closest approach. That's when baseline sublimation increases anyway. What made this event notable was that sharp bursts coincident with heightened solar activity were layered on top of the steady perihelion heating. In short, discovery July 1st. Rapid global follow-up within days, abrupt activity episodes through the summer. Then, the key heating peak as it moved into the late October perihelion window. Observability note: some ground stations experienced temporary loss during solar conjunction or poor geometry. So the dataset has gaps, but the combined space plus ground coverage is dense enough to tie brightening spikes to specific intervals. That timeline discovery, immediate follow-up, abrupt spikes. Perihelion approach is how we know this wasn't a slow seasonal rise. It's an externally amplified, time-locked reaction. Models give 3 practical scenarios and clear observational signatures for each. Continued swelling most conservative. If outgassing keeps up, the coma scattering area grows further. The light curve continues a steep rise, and spectra keep showing strong volatile lines with steady dust production. Imaging will show a persistent, bright coma and a long, dense tail. Photometry will keep doubling on short timescales and non-gravitational acceleration terms. In orbit, fits will remain measurable and stable. This outcome is a prolonged observational bonanza. Lots of data. No structural failure, plateau stabilization. If the volatile reservoir feeding the spike is finite, or surface layers resettle, production rates fall back to a new steady state. Observationally, you'll see the light curve flatten, spectra weaken toward baseline ratios, and particle size distribution shift as large grains dominate. The coma remains large, but slowly fades in relative brightness. Orbit residuals from outgassing reduce. This is still scientifically rich. It shows transient layering or localized vents, not catastrophic breakup fragmentation, failure most dramatic. If internal stresses or thermal gradients exceed structural strength, the nucleus can fragment. What that looks like. Sudden spikes, followed by rapid declines in nucleus-centered brightness, multiple nucleus fragments in high-res imaging, and complex tail morphology as fragments produce independent dust streams. Photometry becomes noisy, and orbit fits show changing non-gravitational vectors as fragments separate. Fragmentation would explain extreme short-lived jumps and is the riskiest scenario for interpretation, higher drama. But also higher scientific return. What to watch in practice. High-cadence photometry to track light curve slope, integral field spectroscopy to watch spatial profiles of species, CN versus metals, high-resolution imaging to look for multiple condensations or jets, polarimetry to probe grain sizes and composition changes. Short checklist for viewers. If the light curve keeps climbing and spectra stay strong, gives continued swelling. If the curve flattens and spectra dilute, gives plateau. If the nucleus splits in images and photometry turns chaotic, gives fragmentation. I'm watching those 3 signals because they give a clear, testable story for what the sun's heating and intermittent solar storms actually did to this interstellar visitor.